So before the break, so we talked about the idea of combining different models, right? If I have many experts, each responsible for some specialization, right? Like it could be partition of the data set, like the decision tree example, or it could be like on a very high level, like on a very high abstract level, so it could be just the topics, right? So let's say if there are many topics in the prediction, and each classifier is an expert in different topic, or a subset of classifiers or more experts in different topics. Okay, so now how do I combine these different models? Okay, so we're going to discuss many ways to combine models today and possibly next week. Okay, so the first simplest approach to combine models is the idea of committees. Okay, so this is very simple. So the basic idea is you consider, let's say, 10 different models or k different models. Okay, like imagine you have k different logistic regressors instead of just one logistic regression model. Okay, now you can take an average of the predictions of all these models. That is my combination. Okay, so like I take 10 different logistic regression model, okay, and compute the average prediction. Okay, now if it is regression, I will compute the average of all the 10. If it is linear regression, okay. Now if it is classification, like logistic regression, then let's say I have 10 different models. 7 of them say yes, and 3 of them say no. So I could just do a majority voting here and say the answer is yes. Is that clear? Now, so this is the general idea. Okay, now there is a small issue here. The issue is I don't have 10 different data sets, right? So I have only one data set. So normally what we would do is like we will take the data and we pass it to the model, right? And the model is going to learn the parameters from the data and then probably throw away the data set and make predictions, right? Now I want to train 10 different models for the particular data set or the task that I have in my hand. So how can I do it efficiently? Like if I just use the same data set to train 10 different logistic regression, so then I'm going to get same models 10 times, right? Like so, same goes for naive Bayes. Like imagine I do 10 naive Bayes algorithm, 10 naive Bayes classifiers with the same data set. I get the same. I get the same model 10 times. Like so, there's no use in doing that. So how do I adapt this procedure to make sure that I get 10 different models? Any ideas?
Do the same thing as cross-validation, like but this time could I vary just one chunk of the data, so the data will be different.
Okay, so you divide the data into chunks and train different classifiers in these different chunks. That is one possibility. Anything else? But then the problem with that is like you have hard experts here again, right? Like so you're kind of dividing the data set in much more harsher way. So there's not a lot of knowledge sharing that is happening. Yeah.
Use different attributes for different models, not using the whole.
Okay, that's also a good solution. Like so, use different attributes for different models. But again, the problem is there is not a lot of interaction between the attributes now, right? So maybe it is important to consider 2 attributes together than separately. Yeah.
You could vary the hyperparameters in the models.
Yes, that's a good idea too. So like you can vary the hyperparameters of the model so that you get different classifiers. Now, for most of the linear classifiers, right? Like so the solution is always same. There's only one solution. So that is not going to help you. But for nonlinear models, yes, that is a good idea. Well, I think we have a lot of interesting ideas here. So none is right, none is wrong. Like so, like something works in some setting. Okay. So, however, the technique that we are going to see today is probably much more generalized than these things, like with less limitations, which is the idea of bootstrap datasets. Okay. It's a very simple idea. So let's say I have n data points. Okay, let's call them as x1 to xn. Okay, now I can create, let's say I want to train 10 models. Okay, I can actually create 10 data sets. Okay, let's just call this as data, capital D, just the data set. Okay, so I can actually create 10 different data sets of the same size, capital N, but by sampling with replacement. Okay, so imagine like data set 1 is, just for simplicity, let's say there are only 10 data points. Okay, now my data set 1 is sampling 10 entries with replacement, which means probably the first sample could be x2, the second sample could be x5, and the third sample could be x2 again, fourth could be x7, then x10, and so on. Okay, so the most important point here is like we are sampling with replacement, which means for every data set there's going to be some examples repeated and some examples excluded. Okay, so I'm kind of creating artificial variations between all these 10 data sets. Now I train 10 different logistic regression models or naive Bayes with these 10 different data sets and combine their predictions. Is that clear? Right? So this idea of generating or coming up with new data sets from the existing data set, right? So this is bootstrapping data sets. Okay, so we're going to do bootstrap data sets, construct k different data sets, and then we are going to combine these models from k different data sets. Is that clear? So this algorithm, like the idea of creating bootstrap data sets, training 10 different models, and combining their predictions, right? Like so this is known as bootstrap aggregation. Okay, or in other words, just bagging. Okay, so this was proposed by Draiman in 1996. It's one of the fundamental ways of combining models. Okay, so like the idea of bagging. So now, for example, let's just consider regression. Okay, I'm going to do bagging for regression. Okay, now let's say I have m different bootstrap data sets. Is that right? And I'm going to train m different linear regression models. Let us call them as ym of x. Y of x is my linear regression, but I'm going to index it with ym of x. Is that clear? Now, for the committee's prediction, is given by y committee of x. Okay, it's simply in the case of regression is an average of m different predictions, right? So this is going to be 1 over m, summation over m is equal to 1 to capital M, ym of x. Is that clear? Now, if you are just using one regression algorithm, your answer is going to be something like y of x. Instead, I'm using m different algorithms and I'm combining their prediction. Okay, so for the next 5 to 10 minutes, we are going to argue that this is actually better than just using one algorithm. Okay, so we are going to have better performance, or at least same performance, but mostly better performance than like just using one model. Okay, so why is that the case? Let's see. Now, suppose, let's say the regression, the true regression function, the regression function that we are trying to fit is h of x. Okay, so whenever you have a model ym of x, this model is going to make some error, right? So let us just decompose the true prediction and the error. So this is going to be h of x plus epsilon m of x. Okay, where epsilon m of x is the model's error. So if you have a model with 0 error, then the output is just h of x, the true value. But if there is some error, it could be +2 or -2, whatever, like that is in the part of the error. Is that clear? Now, what would be the average sum of squared error for one model? Okay, so for one model ym of x, the average sum of squared error is the expected value of ym of x minus h of x, the whole square, right? Now, we know that ym of x is h of x, so this is basically expected value of h of x plus epsilon of x minus h of x, the whole square, right? So these cancels, so this is nothing but expected value of epsilon m of x, the whole square. Sorry, the square is inside, right? So if you have only one model, then the average error of that model is expected value of, like sum of square error is just expected value of the square of the model's error. This is very reasonable, nothing fancy, right? So now let's compute the average error made by the committee. Okay, maybe before the committee, like let's talk about the average error. Before that, let's talk about the average error made by the models acting individually. Okay, so if the models act individually, okay, they're going to get their individual errors. Now I can take an average of all these errors, right? Like, so that is given by, let's say, E av, which is just average of summation over m is equal to 1 to capital M, expected value of epsilon m of x, the whole square. So this is when you have m different models, they act individually, you compute the error, and this is the average error. Now we can compare this with actually the error by the committee. Okay, now the error by the committee is given by expected value of the committee's prediction minus h of x, the whole square, right? So the committee's prediction is given by 1 over m summation m is equal to 1 to capital M ym of x minus h of x, the whole square. Is that right? So previously, when you had only one model, the model's prediction was ym of x. Now we have a committee of models. They are doing bagging. So my model's prediction is given by the average of the committee minus the true function, right? Like, so now let's see what this is equivalent to. So this is expected value of x, 1 over m, summation m is equal to 1 to capital M, epsilon m of x, the whole square, right? Because ym of x, like you substitute what is ym of x, h of x is going to get cancelled. Okay, now I can take 1 over m outside the expectation. So this becomes 1 over m square, expected value of summation m is equal to 1 to capital M, epsilon m of x, the whole square. Okay, so remember that the summation is actually within the square. So in some sense, it's double summation. Like, so it's summation epsilon m of x twice, right? I can actually expand this. So this becomes 1 over m square, expected value of, okay, well, maybe I'll bring the summation outside. So summation m is equal to 1 to capital M, summation n is equal to 1 to capital M, expected value of epsilon m of x, epsilon n of x. Is it right? Right? Now, I'm going to make a couple of assumptions here. Okay. Now, the first assumption that I'm going to make is the mean error is 0. Expected epsilon m of x is equal to 0. Errors have 0 mean, okay, which is a reasonable assumption to make. But I'm going to make a slightly stronger assumption, which is the errors of different models are not correlated. Or in other words, expected value of epsilon m of x, epsilon n of x is equal to 0 if m is not equal to n. You take two different models, the errors are uncorrelated. Okay, this is a very strong assumption. Okay, so we will realize that it is strong like once we finish the whole process. Okay, now if I make these two assumptions, okay, then I can actually take what is here and write it as follows. Like, so this is basically 1 over m square, summation over m is equal to 1 to capital M, epsilon x of epsilon m of x square. Okay, so what did I do? There was a double summation here. So whenever the double summation doesn't match, it's 0. Whenever the double summation matches, then it is just epsilon m of x square. Okay, now this ecom is nothing but 1 over m of E average. Okay, so now this is a very strong reduction, right? Like so what this simple derivation tells us is, instead of treating m different models individually, if I combine them together, then the average error of this combined model is 1 over m times the average error of these individual models. Okay, now this looks very attractive, which means I can just keep adding new models. Like I can keep adding more models. The more models, the error is going to reduce, and maybe it goes to 0. Is that true? So can I just add as many models as I want?
The average won't go up.
Sorry?
The average may go up if the model is bad.
But we are not doing bad models here, right? So let's say I have many good models. Can I just combine them all? And is it going to for sure reduce? Yeah.
That's also competition between the models.
Yes. So the very strong assumption that I made, that the errors of two models are not correlated, right? That is rather satisfied in practice. Okay, because especially because of the way in which we are constructing this. We are constructing these data sets by bootstrapping, right? So if you think about 10 different data sets, they are not really 10 different data sets. There is a strong correlation between these data sets. Like only some examples change, right? So in some sense, this is kind of like an upper bound. But we seldom reach this upper bound. Okay, so like in practice, as you keep increasing the number of models, at some point you're going to saturate. Like there is no new model that you can put in. Like as you said, like there's going to be redundancy. So you will stop seeing reduction in error. Okay. Now, here is an interesting question. I started with, let's say, 10 logistic regression. Okay. I combine them together. My error ecom is better. Like the error reduces. Right? Now, if you remember our discussion about the characteristics of errors, there are three main sources of error, right? My error is a combination of bias square plus variance plus noise, right? Now, which of these three components is reducing? Or is it all the three components that are reducing? Any answers? Any answer in chat? So am I reducing the noise? can I reduce the noise?
No.
It comes from the nature, right? Like, so I cannot reduce it, so forget about it. There is bias and variance. So when I say adding models reduces the error, is it reducing the bias or it is reducing the variance? Variance, why? Why not bias?
Because it comes from the same data, it's the same model, so
Well, more than the data, it comes from the same model, right? So they are all logistic regressions. So the inductive bias of logistic regression is same for all the 10 models that we have, right? Like, so the bias is not touched at all. Like, it's the same model. So what is interesting about bagging is bagging can help you reduce the variance. Is that clear? So the error reduction mainly happens because of the variance. Okay, and you can also prove that ecom is going to be always less than or equal to E average. Okay, is that clear? So when you do your like methods like bagging and other in general, most of these committee or ensemble based methods that we are seeing, right? Like, so they are popular contenders in Kaggle competitions. Like, so you can take 10 different neural networks and combine them together. You're going to get 1% improvement. Like, for example, let's say you're in the top of the leaderboard. You want to get that extra 0.5%. Combining models could be your way to do that. Okay, so as somebody mentioned, like, so in the case of neural networks, like, which we haven't seen yet, it's a nonlinear model. You can just do different initializations or different hyperparameters and train different models. You don't need to do bootstrap aggregation there. So we will talk about that next week. Okay, so but for now, like for simple models, you can do bootstrap aggregation and combine these models. You're going to get better error, like better reduction in error. Is that clear? Any questions so far? Yeah.
error is reduced
Sorry?
by training the same model on a subset of the same data. When one model will learn from all the data. I mean, why not learning from all models, all the data, would have a different, I don't know how reducing the data seen by each model improve the performance.
Okay. Well, first of all, you agree that we are not touching noise or bias, right? So noise cannot be reduced. There is no change in bias, so bias is same. So the only place where you can do reduction is in variance, right? Like, so the way in which we are trying to reduce the variance here is like you have a data set. Like, if you think about how variance is defined, like it's based on the average across different data sets, right? Like, so like how is your current data sets condition varying from the average? So you're just making that gap smaller by treating 10 different data sets. Like, it is true that they are not 10 different data sets, but they are 10 variations of the same data set, which helps you in reducing the variance.
Okay, so in some way, in the data sets, there are
You're simulating.
outliers that decrease the performance of the model when they are added to the data set.
Oh, I'm not sure if we can put it that way. It's a bit complicated thing to internalize. So we will take it offline. Like, but for now, let us just remember that the only possible place where things could reduce is the variance. Like, why is it really reducing the variance? We will talk about it offline. Okay, yeah.
When we train the different models and we want to validate them, do we use the same data set to validate all of them, or do we do the same thing after the training?
That's another good question. Yeah, you can use one validation set. That's fine. Okay. Okay. So now we have this idea of bagging, right? So now let's go back to our decision tree story. Okay. Now, a naive way to do bagging with decision tree is just train 10 different decision trees and bag them, right? So combine them. So you can just bag decision trees. Okay. So however, especially for decision tree, it is very difficult to bring variability. Okay, because just changing one or two examples doesn't change the tree structure that much. Okay, so you're going to get highly correlated trees. Okay, so which means like you can try 10 different data sets from bootstrapping. You're going to get almost identical 10 different trees, or in other words, you're really not improving in performance or reducing the variance. Okay, now there are a couple of ways to make sure you have variety of trees. Okay, now the first approach, again by Brayman, is the idea of random forests. Okay, so this is Brayman 2001. Okay, now so here is the general recipe. The general recipe is you're going to use k different bootstrapped data sets, okay, to train k different trees. Okay, however, there is a small twist. So the twist is at each node, okay, instead of considering all the variables for splitting, I'm going to pick m variables at random. Okay, typically this m is going to be much lesser than, or at least lesser than the total number of features. Okay, this is the only change. Like so, in every node, instead of considering all possible features to test, split, I will randomly pick small m number of like features, and I will compute whatever information gain, like or Gini index, whatever I want to do, and proceed. The next node again randomly take them. So this randomization of like picking features in each node, right? Like so, this will ensure us that we have variety of trees. Okay, so in this case, given that bagging reduces variance, it is okay to let the tree overfit a little bit. Okay, so now you will recursively do this until the tree reaches the maximum depth. Okay, in the case of random forest, you don't do pruning, no pruning. Okay, now, so this is the place where you are actually playing with bias and variance. Okay, because as you let the tree grow as much as possible, then you're like you have less bias, right? Like so you have complex tree, right? We also know that that kind of trees could overfit, right, and have high variance. However, by combining many such high variant trees, you're reducing the variance. Okay, so essentially you are trying to reduce both bias and variance together, which is always not possible, right? Like so, you increase the bias, you decrease the variance. You decrease the bias, you increase the variance, right? There is some trade-off. However, like with a random forest, you can individually reduce the bias for all these trees by letting them grow as much as they want, which is going to increase the variance. You take care of the variance by combining them together. Is that clear? Now, for many, many, many years, like since 2001, okay, random forest is one of the most competitive baselines for any problem, okay, in hand, okay, for not for very large data sets. When you have very large data sets, neural networks dominate, but especially for small data sets and medium-sized data sets, and for data sets which has a lot of categorical attributes and so on, random forests are extremely competitive baselines. Even now, there are still a lot of industrial applications where random forests are deployed. Okay, so whenever you try a new problem, if you can do random forest, you must try random forest to see what is the performance. It's a good baseline, like for you to beat if you want to do more complex things. Okay, so always don't start with highly complicated neural network. Like so, if you can do random forest, benchmark the performance, then you aim to beat that with better models. Is that clear? Okay. Now there is another variation of random forest which has even more variety. Okay, which is the idea of extremely randomized trees, or ERTs. So this is Gertz et al. 2006. You see that people were not so crazy like 20 years back. Like, so every major algorithm came after 5 years. Nowadays, every major algorithm comes after 5 weeks or 6 weeks. Okay, so okay, so extremely randomized trees. So this is going to add one more twist to random forest. Okay, if you think about random forest, in every node, you're picking m attributes, right? You pick m attributes at random, right? Once you pick these m attributes, you are considering all possible scenarios to split with these m attributes and pick the best. Okay. Now we are going to further approximate this and say for every attribute, I'm going to randomly pick only one test. Okay. Now there are many ways to split. I will randomly pick one way to split for that attribute and just use the best of this as the testing criteria there. Is that clear? It's really simple improvement to random forests. Now you can continue until a desired depth, or unlike random forest, in the case of extremely randomized trees, we also have a hyperparameter nmin, which is the number of examples you want in the leaf node. Now, once you reach that, you stop. This is a hyperparameter. Okay, is that clear? Now, this is a very reliable method for both classification and regression. You should be able to do random forest, ERTs, everything with sklearn. Okay, even though the assignment only asks you to explore decision trees, like not random forests, but you can do all these things maybe for your competition. Okay, now the smaller the m is, more randomized the trees are, right? So you just pick very few m, you're going to have more randomized trees. Like there's you're creating a lot of noise, and then you are also decreasing this noise by combining them. Is it clear? Any questions about bagging, random forest, or extremely randomized trees? Yeah?
Random tests, when you choose the split input.
Yeah, so for example, let's take income. There are many possible ways to split income, right? I will randomly pick 50K. Like similarly, let's say there is a option of two-way or multi-way. I'll randomly pick one of them, just one of them. Is it clear? Okay, so now this is all one family of combination. Okay, so this is idea of combining things by taking average. Okay, now there is another smarter or more sophisticated way of combining things. Okay, so which is the idea of stacking. So this is by Wolpert in 1992. Okay, this is also known as stacked generalization. Okay, now here is the idea. In the case of bagging, we were just taking a simple average, right? So instead of taking a simple average, so how about I train another machine learning model on the top of all these k different models that I have, which will actually learn how to combine these models' prediction. Okay, so now we are talking about a meta model, right? Like so, now given x, I'm going to pass it through, let's say, 3 different classifiers: C1, C2, C3. Okay. Now, in the case of bagging, I would just take the predictions of all the 3 and just take an average, right? Which also made us to have this extra condition that all the models should be same. Like if you have different, like for example, imagine you have one naive Bayes, one logistic regression, one SVM. So how do you take average of them, right? Like because SVM is not a probabilistic model, right? So it's not very clear how to take average. So in bagging, you will normally use the same model. Okay. However, the idea of stacking is you take these models, now you pass their prediction to another model. We are going to call this as a meta classifier. Okay. This meta classifier is going to make the prediction y hat. Is that clear? Now, well, first of all, the idea looks very elegant, right? Like so, this is the machine learning approach for solving this combining problem, right? Like so, we are learning a model to combine, which is good. there is also an additional advantage. The additional advantage here is now my C1 could be SVM, C2 could be K nearest neighbor, C3 could be naive Bayes or logistic regression, whatever. I can have any model. Like, so the thing is, like, I can actually combine biases now. Like, I can have different models with different biases. They can output whatever they want. SVM is going to output a score. KNN is going to output a probability value. Naive Bayes is going to output a probability value. I would consider this values as input to this meta classifier. Now, for example, my meta classifier could be a simple logistic regression model. Or it could be another K nearest neighbor, whatever. Okay, so we have a lot of flexibility here. Now, the interesting question here is like, how do I train the meta classifier? So we know how to train C1, C2, C3. Now, given that I gave you the freedom of choosing whatever model you want, you don't need to do Bootstrap datasets anymore. You can use the same dataset, train 3 different classifiers. This is easy to do. Now, how do I learn the parameters of the meta classifier? Any idea? Yeah.
Use the predictions from C1, C2, C3 as features and train a model.
Okay. So the suggestion is, let's say I have a training data set, DTR, which has 100 points. Okay. Initially, you had the features X and output Y. This was the data set, right? This is the data set used to train these classifiers. Now I can construct a new data set, okay, which is basically prediction 1, prediction 2, prediction 3. For the first row, like similarly for 100 examples. And the output is Y. Right? I can use this data set to train the meta classifier. Right? Now, is this a good thing to do, or is there a catch? Like how would this model, how do you think this model would perform?
Can be training on the errors from the first model.
Sorry?
If we have many errors from the first models, we can be training these errors with the meta classifier.
Really? Like, so, okay, the answer is like, if you have errors in the first model, we'll be training with the errors, right? Like, so, not really, because like you have 3 different models outputs and you're learning to predict the correct label, right? Like, for example, let's say C1 was a really powerful classifier. It always makes the right prediction, okay? Then this meta classifier can always try to map P1 to Y, right? So you can ignore bad classifiers. So having bad classifiers is not the problem here. Yeah.
It's not actually going to reduce the variance because, as you said, if you had a classifier that's completely overfitting, then it's just going to keep taking the data from the same one.
Yeah. So the big issue here is this particular setup would prioritize or give more weightage to classifier which has already overfitted to the training set, right? So imagine my first classifier is overpowerful, it overfits the data perfectly, okay? Now, for my training set, it will look as if P1 always correlates to Y. However, given a new test set, like I pass it through all the 3, maybe C1 is a terrible classifier for this. However, my meta classifier has learned to ignore these 2 and just use P1, which is a bad thing to do, right? Now, how do I fix this issue? How do I fix this issue? So we have seen a kind of reasonable approach for this in the past. So what we are looking for is like a model, like what we are looking for is a way to make sure that meta classifier prefers models which has good generalization, not good training performance. Yeah.
User regularization.
I'm not sure how regularization is going to help here. Any other answers? So we care about generalizing models, not overfitting models, right? Which means this data set should not be constructed with training data. This should be constructed with validation data, right? However, we know that validation data is typically smaller when compared to the training set. So this is where the idea of k-fold cross-validation again comes into picture, okay? So I can take my data set and divide it into, let's say, 5 different parts, okay? Now, for each model, let's say M1. For M1, I'm going to construct the model's prediction, okay, which is P1. Similarly, for M2, we're going to construct the model's prediction P2. Similarly, P3, and this is the data set for the meta classifier, right? Now, here is a small change. So I'm not going to train with the entire data and make predictions, okay, because that is training performance. What I care about is the validation performance, right? So I'm going to train with the 4 parts and fill the prediction for the 5th part. Okay, then I'm going to repeat this process again. So I don't think I can erase it easily. So let us just draw on the top of it. So then I'm going to use this part and this part. Okay, it's really bad. And fill this part. Is that clear? So basically, to construct the data set for the meta classifier, I'm going to train each model k times. Each time, I make prediction for the unseen part of the training set. Now, this constructed feature for class 1, right, like for the classifier 1, it is not a representative of training performance. It is a representative of the validation performance. Now, if it so happens that P1 is highly correlated with Y, it's a good thing to overfit to that idea, right? Like, because we know that P1 is better generalizer. So it is okay to overfit to P1 to Y. Is that clear? Any question about stacking? Any question?
To teach this stakeholder validation, what we do with the validation set?
Well, there is no validation set here. This is all training set.
Yeah, but you put away one chunk of the data as a
Yeah,
validation.
so like for example, for the ping case, you put the 5th chunk as validation, right? So you will just train with the first 4 chunks. You come up with the model, use the model to predict the 5th chunk. So that is what goes to the data set of the meta classifier. Then for the green fold, right? Like, so you train model with all the 4 parts which are green. You make predictions for this part. Oh, sorry. I think the green should come here, not there. So this is probably, let me see if I can erase this easily. So the green is for this. Similarly, you fill the whole thing. Is that clear? Any questions? So, well, so far we have seen 2 approaches for combining models. Like, so the first approach was the idea of bagging. The second approach was the idea of stacking, right? So we will stop here, and next week we will talk about another approach to combine model, which is the idea of boosting classifiers. Okay, so that would conclude our discussions on combining models. So then we will move to nonlinear methods. Like, so we'll start with neural networks. Okay, so for now, I think you should have everything that you need for doing assignment 3. So random forest was not yet covered, but now it's covered. So you have everything for assignment 3. So, and also once we cover neural networks next week, like you have everything or most of the things that you need for the competition. So we will stop here. And as usual, this is my office hour.